Right, so good morning, afternoon, and evening, everybody. Thank you so much for connecting to this NfoLD seminar series. We are aiming for having a seminar series every other month. However, if you want to speak or know somebody who would be willing to speak and share their knowledge in the whole life detection field, please have them contact us at contact.nfold@gmail.com. Today, we're very privileged to welcome Dr. Svetlana Shkolyar, who will be speaking to us about in situ biosignature searches as Raman and fluorescence spectroscopy, challenges and recommendations for the Perseverance Rover, also known as Percy, from what I learned. And so every in the month that we don't have a seminar, we have newsletters. So if you have any exciting updates in your groups or papers or other activities that you would like the community to know about regarding life detection technologies, please let us know also, and we'll do our best to share that information. With that, Svetlana, thank you so much for taking the time to speak with us today. I know you have a very busy schedule, so I'm grateful that you accepted to give this seminar. We're very excited for the topic. So the floor is yours. Thanks again.
Thank you, Sanjoy. Thanks for letting me speak to you all today. Okay, so I'm gonna screen share and share. Let's see if this works. Okay. And if I play this, is this okay? Can you see me in presentation mode?
Yep.
Cool. I've got the little sharing my screen notification down here, but I'm hoping that'll go away. If it doesn't, and if that's bugging you, let me know. Okay, so my talk is going to focus on biosignature detections using Raman spectroscopy, as well as what I like to think of as sort of lesser known kind of cousin, fluorescence spectroscopy, a very complementary technique to Raman, which unfortunately isn't really out there as such a useful technique for biosignature detection yet. But I'll show you some studies on Perseverance, how it's relevant to the Perseverance Rover, and how hopefully you can see how both of those techniques sort of in complementarity are very useful together. And although this talk is aimed at Mars analog data sets for, particularly for informing Perseverance Rover, I'd like to encourage you all to think about ways how this might be relevant and applicable to other planetary targets using other types of biosignatures and similar types of spectroscopy techniques in development for future missions. So jumping right in. We are living in an exciting era in planetary science because we are about to put not one, but two Raman instruments for the first time on a planetary mission, as well as fluorescence instruments with the Perseverance Rover, which, as we know, just launched and is going to land in February. The SuperCam and the SHERLOC instrument, which you can see right there. And actually, we were supposed to put 3 first-time Raman instruments on Mars with the ExoMars rover, which was supposed to land roughly the same time as Perseverance. But as we know, that got slightly delayed. So there will be 2 very soon, and very soon 3 Raman instruments on the surface of another planet. On Perseverance Rover, we have the SuperCam and the SHERLOC. And SHERLOC is actually an acronym, one of my favorite NASA acronyms, scanning habitable environments with Raman and luminescence of organics and chemicals. Both of those are actually suites of multiple types of instruments. SuperCam is actually 4 different instruments. It's a LIBS, it's a laser-induced breakdown spectrometer, a Vis-IR spectrometer, an imager, a microimager, as well as a Raman and fluorescence spectrometer. And the SHERLOC is both a Raman and a fluorescence spectrometer with a different excitation wavelength than SuperCam. And I'll get more into why the excitation wavelength is very important in a moment. Raman spectroscopy has been on our radar for multiple decades, as you can see here, for targets, icy, liquid, rocky targets all over the solar system. And we've been thinking about putting these instruments on, as you can see, Phobos and Deimos on Titan. And more recently, with the Europa lander, the science definition team actually defined several Raman instruments in its model payload. And that is a deep UV Raman instrument, which is modeled directly after the SHERLOC instrument, which is a deep UV excitation wavelength Raman and fluorescence instrument, as well as the RLS. Can you all see my arrow when I do this?
Yes, we do.
Okay, cool. The RLS, which is modeled directly off of the ExoMars rover. So why are so many people excited about Raman spectroscopy for planetary biosignature detection? Here's kind of a short, quick list of the pros and the cons. And I don't want to spend too much time on this, but I just want to give you a sense of why this is so valuable on planetary surface. You get basically a unique spectral fingerprint of both organics and minerals, often in sort of two separate parts of your Raman spectrum. So it's very easy to identify at very low abundances, both types of compounds. And for biosignatures, those of you who look at microscale features, like, for example, macromolecular carbon preserved in rock, you will know how important it is to have that context preserved, the mineral context preserved within your biosignature, which allows you to sort of get that, what we call paragenesis, the ability to understand the time-ordered, geological events that happened in that environment that maybe allow that biosignature to flow in, get preserved, get locked into that rock and preserved over time, and basically allows you to understand whether it could be biogenic or not. Now I want to pause here and say that you'll notice Raman does not give you biogenicity. It'll tell you that you have an organic compound, but it will not tell you the origin of that or organic, say abiotic or not. For the Perseverance Rover, however, the mission is a sample caching and a Mars sample return mission. So the idea is that samples containing potential biosignatures will be placed in little, they'll be cored and placed in little caches and then brought back to Earth. And then on Earth, we will use our much more capable analytical facilities and do the biogenicity studies that way. Also, there's no limit to how many times you can, zap the laser off the surface of a sample, and as opposed to some other organic identification techniques, for example, on Mars Science Lab, which are limited in the number of containers and cups that you can use for the analyses, and those types of instruments are also often they do require sample preparation, so they are destructive. So you get to powder the sample, and you don't have that context. And perhaps the most important, I should say, peskiest disadvantage of Raman spectroscopy is the fluorescence interference. There's this background effect that you'll often see here. It's kind of just a generic Raman spectrum with and without this background effect, and this sloping background can really overwhelm Raman information, and that is a huge problem for those of us who at least do laboratory Raman, and for particular types of Raman instruments. The reason for that is, let me see if I can just hide. There we go. Oh, wait a minute. I lost much better. Okay, I think this is better, yes?
Yeah.
Okay, great. Sorry, it took me 6 slides to click the hide button. Okay, moving on. The reason why fluorescence and Raman are, the reason why fluorescence is such a pesky interference in the Raman spectrum is because Raman is actually a scattering technique. So this is going to be just a super quick physics lesson. Raman is the inelastic scattering effect, and fluorescence is a true absorption. So that means when the laser scatters off the surface of your sample, the inelastically scattered photons are what are collected in your Raman detector. That is a pretty weak process, and it's also a pretty improbable process if you think about all the other things that are happening to the photons, right, that scatter off the surface of the sample. And the fluorescence effect, however, is a true absorption. It's a true electronic state change, and it is associated with an emission that lasts some time. So it has a lifetime associated with it. So that is a stronger process, and it's also associated with a longer lifetime than the Raman effect. The Raman effect is basically instantaneous. It happens, it starts and stops at the laser pulse, more or less. Whereas the fluorescence effect has a lifetime that's roughly nanoseconds to milliseconds. Sorry? Sorry, is there a question?
I don't believe so.
I think somebody just forgot to mute. You're good.
Okay. So that is basically the reason why when you are using a dedicated Raman detector to detect the Raman spectrum, you will often get some of that unwanted fluorescence in a spectrum. Now, I just want to be very clear, because my talk was about both Raman spectroscopy and fluorescence spectroscopy as two separate techniques. And what I want to emphasize is that you can use a dedicated detector to detect the fluorescence portion of the spectrum, as I will show you, as SuperCam and SHERLOC are both going to do on Mars. And you can get complementary information from the fluorescence side of things. But again, I just don't want to cause any confusion right now. I'm just talking about the Raman effect, and I'm talking about the unwanted fluorescence sort of being inadvertently collected in the Raman detector. There are several ways to mitigate fluorescence in Raman spectroscopy, and two of these strategies are going to be used, one by SuperCam and another by SHERLOC. So I'm going to briefly tell you about the one that will be used by SuperCam, and then I actually really want to focus the majority of this talk on the SHERLOC like data sets, because SHERLOC is actually intended to be the primarily organic detection instrument on Perseverance Rover. SuperCam will be able to potentially do biosignature identification, but it is primarily a mineralogy instrument, and so that is why I really want to talk today about the SHERLOC and the SHERLOC analog biosignature studies I've done. So SuperCam is a time-resolved instrument. Time resolution is a way to mitigate fluorescence, specifically when you're using 532 nanometer laser excitation, which is green. And so if you can visualize Raman through time and through intensity space, that's kind of what the two effects would look like on top of one another. Here's your laser pulse, and in time, the Raman effect would be essentially instantaneous. That's what these red bands are intended to show you. And the fluorescence effect, as I mentioned, is this longer lifetime sort of like exponentially decaying effect that rides sometimes on top of, sometimes under that Raman signal when it's present. And so with time resolution, what you can do is you can pulse that laser, and you can use a gated detector in such a way that they're sort of synchronized, and you can gate that detector, you can sort of bracket that SIG collection at just that early part of the signal, and then close the gate at that later part of the signal. And with that, you're basically literally gating out that longer lifetime fluorescence effect. The reduction of fluorescence using this type of time-resolved instrumentation is possible in the work I've seen. However, there are challenges, particularly with sample dependence. It really depends on what kind of samples you're looking at, and the success of that reduction it is, like I said, sample depends. So I'll be excited to see what SuperCam does and how many discoveries we can get with a time-resolved instrument like that on Mars. The other mitigation strategy that will be used by SHERLOC, mitigation for fluorescence, is using an excitation in the UV. And here's a depiction of why that's favorable. So here I'm plotting the Raman effect versus the laser excitation wavelength here, and then this is the intensity. So as you saw before, that the fluorescence effect is super broad. It spans many hundreds of wavelengths, up to like 900 nanometers here. And whereas the Raman effect is just super narrow, super discrete, and weak. And so when you look at excitation at visible wavelengths, here I'm showing you 532, which would fall like in the center here, roughly, smack dab in the middle of this intense hump of the fluorescence signal. You can see why it would overwhelm the Raman effect. And this is true for most visible excitation wavelengths. If you go out to the 632 or the 7, there are a few Raman instruments that can go out to 700s in their excitation wavelength. You'll still have that fluorescence interference at visible wavelengths. SHERLOC is a 248.6 nanometer instrument, and that would fall down here in the deep UV range. And you can see how going down to the deep UV, you're basically going towards the tail end of that fluorescence effect. So you're energetically separating that effect out and bringing out some of that Raman information, because the Raman effect is not necessarily affected by the excitation wavelength, whereas you can see the fluorescence effect is. I want to pause here and just say there's a second reason why SHERLOC is exactly 248.6 nanometer. And that is because it is a resonance Raman instrument, which means that excitation at that wavelength is basically in resonance with the electronic transitions of many aromatic organics. And remember, SHERLOC is intended to be an organic biosignature detection instrument. So being resonant to an aromatic organic is very favorable. Essentially, that means you're creating a resonance enhancement of that Raman vibrational band at that excitation wavelength. And here's where 266 nanometers would fall, and this is the excitation wavelength of a SHERLOC-like UV Raman and fluorescence instrument that I've been using in York University with my collaborators in the lab of Mike Daly and his postdoc Emmanuel Laya. And those collaborators and I have been doing some really great Mars analog work, and I like to think of their system as sort of the next best analog out there to SHERLOC, aside from the breadboard itself at JPL. So let me get into the Mars analog studies I did on this 266 nanometer system with my collaborators at York University. So in this first study, we looked at a variety of Mars analog natural samples, meaning collected in the field, and there's a lot to be said about natural analogs. They're far more challenging, they're nature, so they're far more complex and challenging than anything we can make in a lab. And so we took a wide range of Mars analog samples, and we were looking at our target biosignature, which is kerogen. And we were looking at how the UV excitation wavelength of this system could reduce the fluorescence. And let me just briefly sidetrack and show you what kerogen looks like. So kerogen is basically macromolecular carbon. It is the degraded remains of life on Earth that's buried in the sedimentary record. It does not have to be biogenic in nature. When it is biogenically created on Earth, we call it kerogen, but it's really sort of the umbrella term for this structure, this chemical structure that I'm showing is macromolecular carbon. And it basically forms, it's basically these increased clumps of polycyclic aromatic hydrocarbons, these aromatic units. And it can be more or less aromatic as shown sort of through this spectrum here, depending on a variety of environmental factors, metamorphism, diagenesis, where it is in its burial regime, etc. So the point is that's kind of macromolecular carbon, and that's kerogen when it's biogenic on Earth, and that's the target biosignature that's been preserved in these samples that we are targeting in this system, with this system. And so what you can see in this spectrum is that kerogen has this main band roughly at 1600 wave numbers. And it's more or less visible in all the cases we looked at, along with the main hosting, the main mineral, the hosting mineral that kerogen is preserved within in each of these cases. And you can see that the fluorescence is not really an issue. This sloping background starts roughly in the second half of the spectrum, like maybe after 1700 or so wave numbers, and it's really only prevalent in a few samples. So the good news here is that kerogen and the host minerals that we were targeting were successfully detected in these highly fluorescent samples using UV Raman spectroscopy. And we've looked at these samples in other types of Raman systems, and we definitely confirmed that they were challenging and fluorescent. And now, if you'll notice in this second spectrum, that's not necessarily the case. This is an iron-rich mudstone sample that we looked at, and you can see there's basically no compositional information here aside from some like atmospheric artifacts and things. And this is actually a mudstone that came from the Verde Valley of central Arizona. This is a really cool field site that I explored as part of my PhD work with Jack Farmer. And if you're interested in more about Verde Valley, it's actually a lacustrine playa lake bed environment in central Arizona. And so if you're interested, check out that 2018 paper. And so here's the photomicrograph of that mudstone, and you can see the variety of iron-rich phases in it. And actually, that is the reason we think why we were not able to get any compositional information on both organics and minerals in this sample. So the first conclusion that we were able to reach here is that this mudstone exemplifies a false negative biosignature detection, because we know that there was plenty of organic matter in it. And actually in the astrobiology paper, as part of this study, we characterized some of that organics, so we knew that it was present. And the reason that we were not able to see any compositional information is actually because of strong UV absorption near the excitation wavelength at 266. We think due to transition metal coordination complexes, which are basically absorbing the signal and absorbing the Raman signal as well. We know this is not a new concept that iron minerals absorb near UV excitation wavelengths. The Clutis paper goes into a lot of detail about that. But the question we were asking is, how might this affect SHERLOC? You know, before we panic that we're going to an iron-rich planet to do these UV Raman studies, I think we really need to do more work to look at whether it's an abundance question. Is it the phases? Is it the coordination environments? Is it their distribution, like detrital phases or something in the mudstone? I'm not really sure. And I think a lot of work, there's a lot of room for more work to be done on this. Okay, so moving to the fluorescence spectroscopy side of this same study, I want to now switch gears completely away from the Raman and show you the power of what happens when you harness the power of that fluorescence and actually get a dedicated fluorescence spectrum, and how you can use that to complement your biosignature investigations. So in this first panel here, I'm showing you basically the same sample subset, and we're looking at the same spots as on the last slide, regions that visually had regions of kerogen and that showed us the kerogen with Raman identification. And what kerogen looks like in fluorescence is like this. It basically has a super broad feature that peaks roughly around 425 nanometers in all the samples. And that is because it is, if you basically take the spectrum, like individual fluorescence spectra of a bunch of polycyclic aromatic hydrocarbons, like random ones, and you sum them all together, you're most likely going to get something that looks like this. So we can't really know any more compositional information than that. We just know that that's where the kerogen feature peaks, roughly at 425. And I'm also showing you these gray zones in these two spectra, and this is the range of, this is basically the fluorescence spectral window of SHERLOC. And the reason why SHERLOC's spectral window is basically very, very small, it's basically about 250 to 360 nanometers. The reason why it's just so small is because that is actually the target range where only organic fluorescence is thought to occur. So SHERLOC is primarily an organic detection instrument, and so they did this on purpose, because their logic is that if there's organics, if there's fluorescence in this region, it's most likely stemming from organics, and if it's their inorganic fluorescence would most likely stem from stemming from minerals, would occur way out here past 360. And there is really no fluorescence that occurs below that range. It's very, very rare in mineral samples. And so we would be able to see the tail end of that, sort of like that UV edge of the fluorescent of the kerogen feature if we were looking at it with SHERLOC. So we'd at least know that it's there, even though we wouldn't be able to see its peak. And this signal you can see is contrasted from this other panel where I'm plotting basically what I'm calling other organics. These are regions where we did not target kerogen or visually see it on the sample surfaces where we had the laser spot. These are carbonate and sulfate or mudstone matrix regions where we were interrogating all these cases. And we saw the same signal, which has like kind of a feature kind of peaking around the same area, but it's sort of a doublet. I think there are two bands here. Again, there's really not much more we can say in terms of like composition or anything quantitative based on fluorescence spectroscopy. But one thing we can say is that if you look at that this is the same mudstone sample that I showed in the Raman spectrum on the previous slide, the iron-rich mudstone, that did not give us any Raman information compositionally. Here we are able to say that it does contain organics. So that is a biosignature detection that we were not able to see with the Raman that we did with the fluorescence instrument. So two pieces of good news here are that fluorescence from the kerogen reveals a broad feature that is distinguishable from other types of organics features. And we did detect organics in that mudstone sample with fluorescence spectroscopy when it was unsuccessfully detected with the Raman. And another very useful data set that you can actually get from a fluorescence spectrum that can tell you if you have organics or mineral fluorescence comes from the fluorescence decay lifetime. So the SHERLOC will not actually have the ability to get fluorescence decay lifetimes because it is not a time-resolved instrument, but the SuperCam will. And so let me give you an example of how what we can do in terms of the decay lifetimes using this peak feature right here and looking at its origin. So if you take that spectrum that I just showed and you sort of rotate it, you can acquire that signal in a variety of ways. So this is kind of what that a 20 nanosecond evolution would look like of that fluorescence spectrum, and there's that peak feature here. And if you were just interested in the peak features, you basically what I'm showing you in that last slide was panel B. It's like a single spectral acquisition, and here it's shown over a 20 nanosecond block of time. But in reality, it is, like I mentioned, an exponentially decaying signal that peaks here, and so its evolution would look something like what you see in A. And if you actually did what we call time-resolved fluorescence spectroscopy, meaning if you took a time-resolved sequence of that acquisition, you would get something like this. Like it would basically be a data cube of signals where you use the time-resolved instrument to basically get slices at, like in C, I'm depicting 1.5 nanosecond gates in time. So you would collect over that 20 nanosecond evolution just as before, but you would get like every 1.5 nanoseconds, you'd collect and collect again until you get basically the 20 nanosecond evolution of that signal. And so if you fit an exponential decay curve to that peak feature, you can extract its lifetime, because that's math. And so when we did that for this peak feature in the previous slide, we basically saw the lifetimes were on the order of 5 nanoseconds, which supports an organic interpretation for those features, because organic fluorescence is pretty much on the nanosecond scale, usually less than 100 nanoseconds. And inorganic fluorescence is often on the microsecond to millisecond scale. So that's like a really clear way to differentiate the source of your fluorescence. So in this case, this is good news because here's that feature and we know it is organic in origin. And so the third piece of information I want to show about this UV fluorescence spectral data set is the mineral standards that we looked at. with this study. And so when we look at the mineral standards, again, I'm showing you that gray zone, which is SHERLOC's window, which is theoretically supposed to see only organics. But why am I seeing these features in pretty much all of my inorganic mineral standards? This is not likely to be a contamination issue. We ruled that out. So this caused me to scratch my head for a little bit and ask the question, well, could there be some mineral biosignature mimicker that's appearing in what is supposed to be an organic only region? And so I did a spin-off study asking that question, and it led to some very interesting results. So looking at the material science literature, you will actually see that there are a variety of rare earth elements that can have fluorescence in that window, in that 250 to 360 window. And one of the main culprits is cerium-3+. Cerium-3+ is a common substitute for cations in a variety of natural minerals. It's a substitute for the calcium-1 and the calcium-2 site. So really, things like carbonates, phosphates, variety of common minerals often have some cerium defects. And then the next question was, well, how much of a problem could that be at the landing site of Perseverance Rover? At Jezero Crater. So here I'm showing a map of like basically the major lithologies that we expect at Jezero, and a table of minerals that are commonly luminescent with UV excitation. And so luminescence is a type of fluorescence, so don't get confused by that. So when we look at the major mineralogies that we expect to see at Jezero, we're going to see sulfates, we're going to see carbonates, phyllosilicates like smectites, pyroxenes, and again, these are all, a lot of these are calcium-rich minerals, and so it is reasonable to assume that cerium may be present at Jezero and may actually be detectable by SHERLOC. So, so the next step to this study was to look at, well, okay, let's look at cerium and let's look at organics, and let's first look at their fluorescence spectra and figure out just how much of a problem could this be, just how much of a problem does cerium, just how much does cerium mimic some of these organic compounds. So what we did was we took a bunch of organics that I'm listing here from a variety of different organic categories, and we looked at several cerium standards. Here we looked at some cerium phosphate standards in the bottom two spectra. And the first thing that popped out to us is that when you look at tryptophan, which is an aromatic amino acid, and you look at cerium, you can basically see how much tryptophan looks like that cerium spectrum. Tryptophan peaks at 325 and 340, where cerium peaks at about 320 and 338. But these peak, these wavelength peaks are not necessarily important in fluorescence spectroscopy. They're not really relevant because it really depends on the sort of the coordination environment, the bonding environment of your compound that you're looking at, and just slight changes in that can really shift your peaks. So like these were pelletized organics, but if we were looking at them in solution, they would have slightly different, slightly shifted features. So the point I'm making is that it's irrelevant what the peaks are. They are roughly the same spectrum that we're looking at here, which leads us to conclude that cerium can mimic tryptophan using UV fluorescence spectroscopy. But how much of a problem is that on the surface of Mars, where the cerium is really going to be in much less abundance than in the cerium standard? You know, we were looking at like pure cerium phosphate. So when you're looking at sort of more Mars relevant concentrations, how much of a problem would that cerium be? That was the question we asked here. And what we did was we took that cerium standard and we we took a Mars soil regolith simulant, MGS1, which is the simulant. It's a simulant that was created based on the rock nest windblown sample at Jezero Crater. So we took MGS1 and we basically doped it with cerium at a variety of concentrations shown here. And these concentrations are based on the range of known cerium concentrations in Martian meteorites from the literature that I looked at. You basically see this range. And so when we looked at this large range from 50 to 8,000 ppm concentrations of cerium, the spectrum, you can see, does not change really, except its intensity, but the features don't shift. You see basically the same to the 320 and the 338 nanometer feature at roughly all the concentration. And so what this tells us is that cerium mimics a tryptophan detection with UV fluorescence spectroscopy at concentrations low enough to be expected on the surface of Mars. And the other thing that we were able to extract from the fluorescence spectra, as with the kerogen samples, was their fluorescence decay lifetimes. So when we looked at the range of lifetimes in all of these samples, including the pure cerium standard, we saw that for both of the features, both 338 and the 320 nanometer feature, when we fit both of those to the exponential curves and extracted their lifetimes, we saw lifetimes on the range of 5 to 10 nanoseconds in all cases. And again, remember that less than 100 nanoseconds, that is usually where we expect organic fluorescence only. And so these lifetimes of all the cerium samples, and both bands of them, were in the range common for organics. And the other interesting thing here is that I learned through looking at these other rare earth elements that cerium-containing minerals really have the shortest lifetimes of most other REE minerals, and they're always in the organic range. They're always less than 100 nanoseconds in samples that are natural cerium, synthesized in lab, like ours. So that could be a real problem on the surface of Mars. That could be a real false biosignature mimicker there. And so the final piece of this study involved looking at the Raman data on these same samples, because surely we would get some kind of compositional information from the Raman side of things, right? Well, no, actually no. When we examined all of these samples at all the concentrations with the UV Raman instrument, we basically saw a flat spectrum in all cases. Here is the laser line. This is 0. And this is the spectrum, and with these little zigzag, these little sawtooth features, this is basically an artifact of low signal to noise. It's an artifact of the instrument. It's not compositional information at all. So the point is, there is no compositional information coming from any of these samples. And that that lack of identification of cerium with the UV Raman spectroscopy side is due to strong absorptions in the UV. It's due to strong absorptions of cerium. So again, we're having the same issue that we had with the iron mudstone sample, where the UV excitation wavelength is just causing so many strong absorptions that we're unable to get any mineral information in this case, or organic information. And these samples, I think, exemplify UV fluorescent spectral signal, suggesting a potential biosignature. Both the spectral signal and its lifetime suggest a potential biosignature. So that's 2 data sets that give us that line of evidence, with no additional evidence provided by Raman spectroscopy, which complicates things, because, you know, in biosignature studies, we always want as many lines of evidence as we can before we can really conclude that something is a biosignature, especially when we're talking about Mars and caching that sample for return to Earth. We would want as many, as high confidence as possible that we had a potential biosignature. And so these results would lead to the erroneous conclusion that fluorescent spectra and their lifetimes on these samples would constitute a potential biosignature. And in a sample caching scenario on Mars, this would be a problem. And so that is sort of just a cautionary tale that came out of this last study. And this is a paper in its final stages of revision, and I hope that will be out soon. So if you're interested in that paper, let me know. And with that, I will just briefly summarize. We have seen that Raman spectroscopy does detect organics and their mineral contexts at very low levels of concentration without real sample prep. There are a lot of reasons why, and I hope I've shown why it's favorable for biosignature detection, not only on Mars with the Perseverance Rover payload, but again, maybe in future planetary surface missions as well. We've seen that Raman spectroscopy and fluorescence spectroscopy, when combined, can actually enhance the confidence of biosignature detections. And I think this is the main reason why both SuperCam and SHERLOC are actually combined Raman fluorescence instruments. They give you complementary data. And we've seen cases where both false negative in the case of the kerogen samples and false positive in the case of the cerium samples, detections do occur, especially at UV excitation. And I really think more work is needed to understand how this is going to impact specifically biosignature investigations with SHERLOC. And it is my hope that these considerations improve the future science return of instruments not only like SHERLOC, but again, future instruments to diverse planetary targets as well. And with that, I will say thank you. And as I take questions, I will leave this beautiful image of Perseverance's launch at the end of July and the official countdown to landing clock. So go Perseverance. Thank you.
Great talk, Svet. It's really interesting. For everyone watching, I am going to allow everyone to unmute themselves to ask questions here in just a moment. But first off, there are several questions that in the chat we'd like to start with. So first off, from Dragos Zaharescu. Am I pronouncing that correctly, Dragos? Close enough? Thank you. First off, he wants to know if the samples get affected by the UV laser.
Yeah, that's an interesting question. Normally, yeah, with an excitation wavelength in the visible, what I've had to do is really keep my power low. You really have to just control the power, and that's manually controllable. Yes, with the UV, you are going to get sort of more energy on the surface of that sample, but even though the SHERLOC is not time resolved, it actually does pulse the laser. So it is limiting the amount of energy that hits the surface of your sample. So SHERLOC does have a sort of mechanism in place to reduce the energy on the surface of the sample. And in my work with the UV system, I have not seen any surface degradation, and neither have my colleagues in the lab in their studies. So you're right. You're absolutely right. It can be a problem, but we're mitigating it.
Interesting. Dragos also wants to know about the metamorphic conditions on Mars. So he says kerogen on Earth is a high pressure temperature metamorphism product. Are there any similar conditions on Mars?
Sorry, can you repeat that? Are there any high metamorphic
high pressure temperature metamorphic conditions on Mars
that would create, in terms of that would create a certain type of organic compound, or geologically, or
so Dragos, you can unmute if you'd like to actually ask.
Right. So my question was, Mars is a different planet with a different gravity. The conditions, the metamorphosis conditions of Mars must be different than the ones here on Earth. So my question was, if there was organic life on Earth, on Mars, would it be impossible to create kerogen the same way we created on Earth?
Yeah, that's a great question. So right, you're right. On Earth, with the metamorphic conditions and with plate tectonics, yes, we do have more burial and metamorphism, and that is how the organic compounds can sort of compact and create kerogen. And on Mars, although we don't think there was plate tectonics, for example, an impact could have produced similar you know, compaction and contact metamorphic conditions. So maybe, yeah, I've thought about this question, and that's a really great question that I don't think I have a satisfactory answer to, except maybe potentially impact, and maybe well, it could have been, the problem is it could have been meteoritically delivered macromolecular carbon, right? And it would look, and it would be on a very, very shallow surface, and it wouldn't have had to have any, you know, burial or metamorphism to create that, what would look like basically very mature kerogen, very old, very compacted kerogen. It could very well be meteoritic in origin. So yeah, that's another way that we could see it on the surface of Mars, and we would only know what it truly would be after a sample return to Earth.
Yeah, that sample so clutch. We have a question from Carol Stoker. She wants to know what the organic content was of the samples that were shown for the SHERLOC analog.
The context of the samples that were shown for the SHERLOC analog.
The organic content.
Yeah, so that's in the 2018, the Shkolyar et al. 2018 paper. Yeah, we did some total organic carbon analyses on those samples. I don't have the numbers off the top of my head, but we did definitely take the samples from that field site in a variety of different facies, from the sulfate to the halite to the mudstone, and we did do TOC analyses on all of them, and all of that is detailed in the 2018 paper, and I can send that out if you're interested.
Awesome. Let's see. We have a question from Alex Pontefract. She wants to know if SuperCam can address any of those issues with cerium.
Yeah. Technically, so yeah, that's a great question. SuperCam is going to be a visible excitation instrument, so it's gonna, you know, the vibrational information is going to be a little bit different with that excitation wavelength. So hopefully, it may be able to identify the minerals. So cerium itself is going to be very difficult to identify with the Raman side of things, because you'll basically get, like, the best Raman will be able to tell you is, like, you have you know, like a calcium phosphate or a calcium carbonate, and then the peak might shift a tiny bit based on the cation. So there may be some specific cases where that cation, like, it's been characterized in databases where it's like cerium or some other rare earth element as opposed to what is supposed to be calcium. But with solid solutions, that's often very, like, you'll get a range of Raman shift, like from, you know, calcium to sodium to magnesium in a sulfate. You can get a pretty wide range of shifts of that vibrational band of that cation. So it may be challenging to say that it is cerium. I do think the SuperCam team is doing some rare earth element studies. I'm not exactly sure what kind they're doing. So I do think they are building up some databases. So we will see. We will see.
That's awesome. So we actually have a couple of questions now concerning kerogen. The first is from Nikki Parento. She wants to know if you've analyzed, like, fresher organics like protokerogens or hapanoids, which is pretty intriguing.
I just realized my video was not on that entire time when I stopped sharing my screen. Sorry, if you analyze hapanoids.
Has your team analyzed fresher organics like hapanoids or protokerogens?
No, we have not. Not with the UV system. The samples that we looked at with the UV system were only the kerogen preserved in the sedimentary sample. So it was basically degraded kerogen, nothing fresher than that. And the only other work I've done on that UV system was what I showed with the organics that we were looking at with the cerium standards. And those were basically lab purchased organics that were palatalized. So no, it would be very exciting to combine forces and do some work with what you're talking about with the hopanes and some of the lipid biosignatures. Definitely, Nikki.
Awesome. Yeah, agreed. Joey, you can ask your question by unmuting.
Yeah, hi. Great talk, first off. That was excellent.
Thanks.
I was curious, so kind of on the subject of kerogen still, and to get to Dragis's issue as well. So kerogen forms in metamorphic conditions, but also forms in the sediment. So kerogen formation starts in the sediment by biodegradation, so you don't need to have heat and pressure for a kerogen formation, which would also mean that on Mars, the most likely form of organic matter is still going to be kerogen. But then kind of to what you were talking about in the iron-rich mudstone.
Mm-hmm.
So that was from a lake, right? A lake system, which means it's
yeah,
likely.
Yeah, previously,
Yeah.
right?
So it's going to be a type 1 kerogen likely. So
Mm-hmm.
if the SHERLOC is detecting, or the UV is detecting the PAH signature, could you just have a really highly aliphatic kerogen so you're not seeing the signature from that?
So the way what you see in a Raman spectrum when you look at kerogen is normally that 1600 band, and in a visible system you'd also see a very prominent band roughly around 1350. It wasn't as visible in the data I showed because as I mentioned, there are some resonances in the UV. So in the UV, that 1600 band kind of swamps out all the other organic groups, and that is that is the vibrational band of like graphitizing PAHs, so the more compacted, the more mature organics. So yes, you could. There are a lot of lab studies where you could look at the Raman spectrum of different maturities of kerogen, and basically what you can see is, and you can even quantify how the 1350 and the 1600 band shift, how they ratio, a variety of quantitative features of the Raman spectrum of kerogen. Yes. I don't think there's been as much work on the UV side as there has on the visible side. So this is more applicable to lab studies. And even with that, there's like a lot of debate between what types of quantifications give you the best information, and how applicable those quantifications are across the diversity of kerogens that you can have. And especially the debate really gets interesting when you look at the younger, the more aliphatic organics. That's the gray area. But yeah, there's definitely some interesting work being done on that, and hopefully SHERLOC will be able to. And if we do get kerogen with SuperCam, yeah, there can be some more said about that.
Great, thanks.
We have a question in the chat from Alta Howells. Can SHERLOC give you a sense of kerogen abundance in the sample, and maybe even go even further to the concentrations of the organics that we're looking at?
I don't think so. I'd like to say yes. There may be some very I'm trying to think of some very specific types of cases, like unless you had organic standards predefined for those compounds, and I don't know that SHERLOC has done that type of database work. I don't think you will be able to say a whole lot on Mars. Terrestrial Raman studies, in the lab, yeah, it would still be very challenging. So the level of complexity would be even worse on a rover.
Yeah, so still that sample return is so important.
Yeah, that's why we're hoping for the samples to be returned successfully.
Absolutely. If anyone else has any questions, you can unmute yourselves to ask. Or go ahead and type in the chat.
I have a question. I have another question. Can any of those instruments at Mars resolve other rare earth elements other than cerium? I mean, there's a whole series. So, I mean, I have a paper on rare earth elements. I put the link in there. You can check it out. Actually, it's on biosignatures, using rare earth elements as biosignatures.
Mm-hmm.
So I found patterns in the distribution and differences between rare earth elements, right? So associated microbes, plants and fungi. And I was wondering if you can detect elements other than cerium and the rare earth element series. Right? There are many. There are 11, 12, 13.
Mm-hmm. Yeah, so that's a great question. And there's another payload instrument which I didn't really talk about, but it is Pixel. It's going to be basically an X-ray fluorescence elemental mapping and imaging instrument. So the idea on Mars is actually, with Perseverance Rover, is actually to use both SHERLOC and Pixel data sets sort of in combination, where you would look at a spot And if it had some sort of interesting, organic or some other potential biosignature signal, you could do a pixel map and a SHERLOC map. You could actually get like pixels of,
like
spectra
maps,
and create
like
a map.
elemental maps.
And
Right.
yes, you could do that both with the Raman vibrational bands, and you could do that with elemental maps with a pixel instrument, and then you could basically overlay those pieces of information. And so what you're getting at, potentially rare earth element enrichments and distributions. Yes, pixel is supposed to be able to get that kind of information.
That's super cool. Yeah.
At the micron level, I believe. Mm-hmm.
Yeah, well, that's another problem, right?
Yeah, it depends on what scale you're looking for. Micron
is another problem.
Yeah,
micron is good enough.
not.
Micron is good enough. Thank you so much.
Thank you.
Awesome. Any other questions? Well, if not, then thank you so much, Svet. That was really intriguing. Really enjoyed your talk a lot. Yeah, this is fantastic.
Thanks.
Thank you again, Svet. It's cool.
Yeah, I'm excited to have you Ask an Astrobiologist next week too. We'll have a
that'll be fun.
more general audience for that, but it'll be fun.
That'll be fun.
Cool. Well, thanks everyone for joining. And thank you so much, Svet.
Thank you, guys.
Bye.
Okay.